Hello students, hope you all are doing very well, and it's so nice to be back to teaching and learning. Though online, this is going to be an amazing experience and will result in fruitful learning for both of us. In semester 5, we have a subject, electromagnetic engineering. Electromagnetic engineering is, I believe, one of the oldest core subjects of this domain of technology. It discusses about theories and concepts based on electromagnetism, and also it gives us an insight and a thorough understanding of all the concepts that are required for today's world of communication. The theory of electromagnetism, in the form conceived by J.C. Maxwell, can boast 130 years of honorable service. It has withstood the severest tests, proving itself to be for completeness and elegance among the most solid theories. So it is going to be fun learning this subject. I should mention at this point of time that this subject is slightly heavier on the mathematical aspects, but it is simple mathematics and it is based on some very simple prerequisite mathematics which you have already studied. Firstly, it is vector analysis. Secondly, the coordinate system. Now, I'm sure each one of you has gone through a course of vector analysis, and vector analysis provides the mathematical tools that are necessary for expressing and manipulating vector quantities in an efficient and convenient manner. Now, to specify a vector in three-dimensional space, it is necessary to specify its components along each of the three dimensions. That is why an understanding of the coordinate systems is very important for us before we actually start dealing with concepts of electromagnetics. Why does it make understanding better? Because I need to visualize while I solve problems. So an understanding of coordinate systems makes this visualization easier. Coordinate systems are defined as arrangement of reference lines or curves used to identify the location of points in space. Now, with this definition, let us look into the types of coordinate systems. Let me be specific here that we are dealing only with orthogonal coordinate systems. Okay, and they are called orthogonal because they are mutually perpendicular to each other. That is, the axes of the coordinate system are mutually perpendicular to each other. And the most commonly used coordinate systems are Cartesian coordinate systems, which we also call as rectangular coordinate system. We also have cylindrical coordinate systems, and finally the spherical coordinate systems. Now, in study of vector quantities, we use all these three types of coordinate systems. So one may ask, how is that I choose a coordinate system? How do I know which coordinate system do I apply while I solve a problem? Well, the answer to it is a particular coordinate system is usually chosen to best suit the geometry of the particular problem under consideration. Like for example, if I'm dealing with a problem of a spherical object, then it's convenient for me to work in spherical coordinate systems rather than cylindrical or Cartesian. Likewise, if I'm dealing with a problem where I have, if it's just a line, and let me be clear, not a pipe kind of a structure, just a simple line, then it's easier to use Cartesian coordinate systems. Or maybe someone may choose cylindrical coordinate system. So likewise, we choose the best suited geometry depending upon the problem in hand. Vector algebra governs the laws of the mathematics that goes in solving these problems. Now, it's also important for us to understand that in order to describe a vector accurately, some specific lengths, directions, angles, projections, or components must be given. The coordinate systems help us with this. In electromagnetics, the physical quantities we deal with are in general functions of space and time. A 3D coordinate system allows us to uniquely specify the location of a point in space or direction of the vector quantity or compute parameters with accuracy. Now, before we move ahead, let me also tell you that there, there are non-orthogonal coordinate systems as well. Okay, but we restrict ourselves to orthogonal coordinate systems because the non-orthogonal coordinate systems are very specialized. Okay, the next question one may ask is, having said that there are three basic types of coordinate systems like the Cartesian, cylindrical, and the spherical, what is the need for more than one coordinate system? A point in space has the same location and an object has the same shape regardless of which specific coordinate system is used to describe them. The solution of a given practical problem can be greatly facilitated by the proper choice of coordinate systems that best fits the geometry of the problem. And hence, there is a need for more than one type of coordinate system. Okay, so now let us consider a two-dimensional Cartesian coordinate system or a rectangular coordinate system. So here this is something that you are familiar with, but quickly I'll take you through it. So if I have a point P, okay, in this coordinate system, so I can say that this point P is at some distance x1 away from the origin, and it is at some distance y1 away from the origin. So the location of this point can be very easily mentioned that it is at x1, y1. Okay, that's quite simple. But if the same point has to be now represented in a three-dimensional way, then what do we do? Then I introduce another axis. Okay, so now let us consider a three-dimensional axis. So what I'm going to do is I'm going to consider, okay, three axes. Okay, so this is my x-axis. I call this as x-axis, and I have here y-axis. Okay, and here you have your z-axis. Now notice that I have changed the positions or alignments of these axes. X and Y are in the horizontal plane. By horizontal plane, I mean that they are parallel to the Earth's surface. Okay, so they are in the horizontal plane, and the Z axis is perpendicular to both X and Y. Okay, and normally this is the generic denotion. Z is always taken along the vertical axis, which normally depicts the height of an object, and you have the length and width being represented by along x and y. Okay, but if you are comfortable, you would like to take it in some other, you would like to take height along x, you're free to do so. So there's no restriction, but this is a generic way of using it, but you are free to use the way you want. Okay, so now I have the origin here. Now what I do is I'm going to take the same point P. Okay, now this point P, I have it here. Okay, I just want to know how am I going to locate this point. Okay, so it's easier if I start with Z. So I say that this point P is at some distance, Z1 away from uh, the origin. That means it is placed at some height. Okay, and that height is Z1. Okay, then I will say that it is some distance away along the x. Okay, distance away from x, so that distance is x1, and finally it's some y1 distance away, so that's y1. So now in order to define your point, I need x1, I need y1, and I need z1. So I need three parameters, one along x, one along y, and the other along z, to define a point. Okay, so what we have done now is we have defined a point in a Cartesian coordinate system. So now we have to see what are the unit vectors and how do we define the differential lengths, the areas, and volume. Okay, so now I'm going to use a software which will aid my teaching and your understanding. And I'm going to switch between the software and my whiteboard. The software is an EM simulator. It is ANSYS HFSS software. It is typically not used to explain coordinate systems, but since it's a modeling software, I have coordinates there and it makes our understanding easier. So now let's just move on to our HFSS software. So here we are with in our HFSS environment. So here you see the three axes x, y, and z, which is vertical. Okay, now we are going to discuss what we call as constant planes. Okay, so what are constant planes? Suppose I walk around at z equal to 0. Okay, I'm at z equal to 0 and I walk around everywhere along this plane. Okay, so let me just introduce that plane for you. Okay, I've introduced a plane. Okay, um, so this anywhere that I walk around on this plane, the value of z is always going to be 0. Okay, because I'm at z equal to 0 plane. So now this plane is called as the z constant plane, or it is also called as z equal to 0 plane. Also, alternatively, it's referred to as an xy plane because it is only variables are x and y while you walk over it. Okay, so is our xy plane. I'll now introduce another plane which is again a z constant plane. Okay, so you have one more plane which is at some distance away from the origin at some height. Okay, so now this is also a z constant plane. I have fixed it at some value of 1, at a value of 1. So z is equal to 1 here. So will be called as z equal to 1 constant plane. So as long as I'm walking on this, moving around on this plane, the height at which I am is always going to be the same, and that height here is 1. Okay, so this is the z equal to 1 plane. Fine. Again, it can be referred to as an xy plane. Okay, so now let's introduce another plane, and this plane will be along the xz. So that's called as the xz plane. Okay, so this xz plane will now have a value of y which is equal to 0. Now, why do I say it's at 0? See here, it's along y equal to 0. Okay, behind this, it's nowhere behind it. Okay, so it's along y equal to 0, and so it is called as a y constant plane, or it is also referred to as y equal to 0 plane, or it's also referred to as the xz plane. Okay, so we first studied about the xy plane. Now it is the xz plane. Now I'm now going to introduce um, another plane. Okay, so this will be our third plane. This plane is now having a value of x which is constant. Okay, okay, this has a value of x which is constant, and okay, so this is also called as the zy plane or x equal to constant plane. In this case, since x value is at 0, it is also called as x is equal to 0 plane. Now, instead of this three planes which intersect to make a corner, instead, if we had used a cube, then how would it look like? Okay, then how many planes do you have there? You have 6. So in case of a cube, okay, what you see here, I have now just brought in a cube as well. Fine, so let me just make it, unhide it. Okay, so you have your cube as well. So you see a transparent cube. So now this cube, which is actually suspended in air, okay, so you will see that it has a front face, okay, a front face, and it has a back face. Okay, so here none of the faces are at 0. It is at along the x, this is the x axis, so this is at some value of x1, there's a back face, and there is another at x2, there's a front face. On the top you see that there is another face which is, we call, that's again on the an xy plane. This is an xy plane. Okay, and the bottom is also an xy plane. On the right side you have a zx plane, and on the left again a zx plane. Okay, but their positions are different. So this is about planes. It's very important for us to understand what are planes, because that's going to be useful in our further discussions. So now you see that I have brought the same box over here on the slide, and now we'll discuss two very important things here. One is the unit vector and the other is the differential length. So let us start with the unit vectors. Okay, unit vectors are vectors which carry the information of direction of the vector. Okay, so unit vector is denoted by a bar. Okay, a small a with a cap on the top. If it's along x, then it is ax bar. If it's defined along y, then it is ay bar. And if it is defined along z, it's az bar. Okay, so now let us see how do we define unit vectors here. Unit vectors have a characteristic property that they are always moving outward from the object. I'll repeat, the unit vectors always move outward from the object and are always normal to the object. Okay, so here this is the given rectangle. Let us look at the front face. This is the front face. The front face is the x is actually a yz plane. Okay, and if I draw a normal to this yz plane, okay, if I draw a vector which is normal to the yz plane, that means it makes an angle of 90 degrees with the front face, then this becomes my unit vector along the positive x direction. I repeat this once again. If I draw a vector which is normal to the front face, okay, that means it makes 90 degrees with the front face and it is moving outward in the direction of positive x axis, then it is termed as ax bar. Now, if I now consider the back face, okay, and I draw a vector which is normal to the back face, okay, I now consider a vector which is normal to the back face and it is making an angle of 90 degrees with the object, with the back face, and it's moving outward. So when it moves outward, it is moving in the negative x direction, and hence this unit vector will be given by minus ax bar. Likewise, on the right hand side, you have this face. On this face, you can now define a unit vector along the positive y direction. So that is ay bar, because it is normal to this face which is in the xz plane and it's moving outward in the direction of positive y, positive y. So likewise on the left face, okay, if I now consider the left face, I have here a unit vector which is a y bar. So now coming to the top face. The top face unit vector will be moving upward. It makes an angle of 90 degrees with the top face, and because it is along the positive z direction, it is az bar. Likewise, I will have a unit vector in the negative z direction from the bottom face. So this is about unit vectors. Having defined unit vectors, it is now time for us to define the differential lengths. Let's consider that the length, width and the height of this box is small. It is differential. Okay, when I say differential, it means it's small. Okay, now how do I define lengths? If the length is along the x-axis in the direction of x, then it is given by dx. Okay, so this is your dx. If the length is defined along y, then this is given by dy. This length is dy. Likewise, you can define dz as the height of the box. Now you must be wondering, why do I write dx, dy and dz? Okay, like I mentioned, the size of the box is small. It is just differential, or you may call it as incremental. When you have a small quantity, you call it as in terms of either dx or dy or dz. Fine. Okay. Now this is about the differential lengths and the unit vector. So until now we have defined a point, the unit vector and the differential lengths. So we now move ahead to define the differential areas. So how do we define differential areas? Okay, now what do we do is, let's calculate the area of the front face. Okay, so it's, we know the formula for the face, for a plane. It is length into height. Okay, x into y. Okay, so likewise for the front face, the area will be given by, this is your dy and this is your dz. Okay, so for the front face, okay, I'll call it as dA is equal to dy into dz. Okay, now I also have a back face. The back face, what's the area of the back face? That is also dy into dz. Now when you're talking to someone, how do you, and you're talking in terms of just dA, how do you recognize by looking at an equation as to whether it is on the front face or whether it is the area of the back face? Okay, now in order to differentiate, what we do is, we will say that the front face has an associated unit vector and the unit vector is ax bar. So I will now define area, which is actually a scalar quantity. I will make it a vector quantity by associating a unit vector along with it. So now dA becomes dA bar, which is equal to dy dz ax bar. So this is for your front face. Likewise, I have a back face. Now for the back face, how do I define it? I'll say again dA bar, which is equal to, remember the back face has a unit vector which is in the direction of minus ax bar, because the unit vector goes out in this fraction. So it is minus ax bar. So I have dy into dz into ax bar, but ax bar has a negative sign which I will write here. Okay, so in general I can say the area vector dA bar. Okay, now because this is associated along the x direction, the unit vectors are along the x direction, I can also call it as dAx bar, which is equal to plus minus, I mean plus minus here, dy into dz ax bar. Now remember, suppose you just don't write the unit vector, but you simply say dAx is equal to dy into dz. The subscript x stands for the direction of the unit vector. But when I don't write the unit vector on the RHS, I will not include the vector sign for dA. I'll only consider its magnitude, and I'll say this magnitude is along the x direction and it has a value of dy into dz. Remember that the positive or the negative sign is associated with the unit vector and not with the magnitude. Just as we define the area or the area vector for the front and the back faces, we can define the area for the other faces as well. So now let us consider the right and the left faces. So left face, okay, let's consider the left face. Okay, so the left face is here, fine. So I can say dA bar along the y direction because the unit vector is along the y direction, fine. So this is given by what is this is dx and this will be dz. So dx into dz along the ay direction. Likewise, I have the right face. Okay, the right face will be day bar is equal to, sorry, here ay has an associated negative sign. So this is here plus dx into dz ay bar. How's the unit vector? It's this. Okay, so this is your ay bar. This is minus ay bar, right? Okay, so now let us go. Let us just write its cumulative form. Day bar will be equal to plus minus dx into dz ay bar. That is, the magnitude is dA y is equal to dx into dz. That's the area, magnitude area. Okay, so now we consider the top face. So the top face will be given by dAz bar because the unit vector here is z, so that's your az bar. It's positive in direction, so you have plus dx into dy az bar. Okay, and now coming to the bottom face. So bottom face will have, so you have for the bottom face you have daz bar which is equal to minus dx into dy az bar. Again the negative sign is associated with unit vector. So I can now write daz bar is equal to plus or minus dx into dy az bar. That is, I have daz to be equal to dx into, okay, I ran out of place. I have dx into dy. That's the magnitude. Now, another way of looking at these areas is that when you say dAx, it means that it's the area of a plane where x is constant. And when you say day, you mean that it's area of a plane where y is constant. Likewise, daz is the area of the plane where z is constant. Okay. Now, having understood the area in its magnitude and also its vector form, it's now time for us to define the differential volume. Okay, so we have defined the point which is defined by xyz, unit vectors given by ax bar, ay bar and az bar. we have differential lengths given by dx, dy and dz, and the areas are in front of you. So then in that case, what will be the volume? So the differential volume is nothing but the product of the three differential lengths. So differential volume is given by dV, which is equal to dx into dy into dz. Okay. Now finally, we are left with the vector differential length. Now these differential lengths that we have seen here, these are only the magnitudes. These are magnitudes. Now, if I have to convert dx into a vector quantity, okay? Now, if I had to convert dx into a vector quantity, I would associate it with a unit vector. So, magnitude dx, okay? So, this is the magnitude, and I'll associate it with a unit vector which has to be along x direction because my dx is along the x direction. So this guy ax bar is nothing but your unit vector. Okay, so dx is transformed into dx ax bar. Likewise, you will have dy ay bar and dz az bar. Now, what is vector differential length? Differential length individually along different directions, along the three directions, is dx, dy, and dz. But when I now say vector differential length, I mean, I'm going to write differential in a short form. So, vector differential length is dl bar, which is given by sum of the vectors along all the three axes, or you can say sum of the components of the vectors along the three directions. So I can say dx ax bar plus dy ay bar plus dz az bar. This is the vector differential length. Okay, so this completes our discussion about Cartesian coordinate system. Likewise, we will also be considering cylindrical coordinate system and spherical coordinate system. Having thoroughly understood our Cartesian coordinate systems, it's now time for us to move on to cylindrical coordinate systems. These cylindrical coordinate systems are nothing but three-dimensional version of the polar coordinates of analytic geometry. Now, just as we defined in the Cartesian coordinate system, we are going to define a point, unit vectors, differential lengths, differential areas, differential volume, and vector differential lengths for cylindrical coordinate system. So now let us consider a cylindrical object. I have considered here a hollow pipe, and this is deliberately done so that it helps our understanding. I've not considered a full cylinder. Okay. Now this cylindrical pipe, okay, has some thickness. Fine. Now we first start with our task of locating a point or defining a point. Okay. Now let's bring in a point. The small yellow ball that you see is our point. Okay. Now, how do we define this point? Now, since I have placed it here, you know that this cylinder has some radius, and this guy, our point, is sitting on the rim of your pipe. So let's say it is at some radius r. Okay, this outer face of the cylinder is at some radius r away from the center axis of the cylinder. Now, who forms the center axis of the cylinder? That's the z axis. Okay, now, so radius becomes one important piece of information which helps us define a point P. The point P is our yellow ball. Okay. Now, which is the next easiest option? Let's first do the easier ones. We'll just then go over to the next. Okay. So the next information that I have, which is easily conceptualized, is the height. Let's say it is at some distance z away from the lower bottom. Okay. Now, where's this lower bottom? Where's the lower base of the pipe? The pipe is sitting over a plane which is z equal to 0, or you can say it is a z constant plane where z equal to 0, or we know that it is also called as the xy plane where z is equal to 0. Okay. Now, this gives us the height information and the radius. Now, with this information, so now let us just add our height guy also. Okay, is this information enough for us to define a point? Let's see why is it not enough. Okay, now this point P, it's here. If I say the point is at some radius and at some height on the cylinder, so you will identify this point, or you may identify the point to be somewhere here. Okay, a point, the same point, if it is placed here, then it will be at the same radius away from the z-axis and it will be at the same height. Likewise, if I say that the point is over here, then this basically is at the same distance r away from the z-axis. Okay, and it is at the same height z, right? So I will not be able to categorically define as to where along the rim of the cylinder is this point placed. So I need to introduce another guy, and that guy is our phi. Okay. So here is our phi. Okay. I just mentioned r phi z. Okay. Now I have introduced a plane. You see that this plane, one edge of the plane is along the z-axis and this guy is making an angle, and let's call this angle as phi. He makes an angle phi with reference to the x-axis. Okay. Now, remember that phi is always an angle with reference to the x-axis and no other axis. Okay. So he moves basically in this fashion. He moves in the anti-clockwise direction. Now this angle phi that this plane makes, okay, defines our point completely. Fine. So now you can say categorically that the point is placed at this radius. It is placed at this radius away from the z-axis, and it is at this height z from the xy plane, and it is at this phi. Okay, intersection of all these three planes is going to define our point P. Okay, now let us understand little more about our phi constant plane. Okay, and that will give you more clarity as to what I have been talking. Fine. Now for this, I had to come back to HFSS. Now in HFSS, I'm going to demonstrate to you how the phi plane is going to go around. Okay. Now the phi constant plane, I said, is always defined with respect to the x-axis. Fine. Okay. So let's start with its position at the x-axis. Okay. So you have a plane at the x-axis. When you probably shift it little more, it makes another angle phi 1. Let's say this is phi 1, and you have phi 2, and then it moves further. It's going anti-clockwise. So you will see that this guy goes around like this and completes how many degrees? 360 degrees. Let's see this once again. Okay. So it's beginning position and it goes around like this, and it is now completing its 360 degrees. So the phi angle has a range from 0 to 360 degrees. Okay. So now that we have all our three parameters, excuse me, let's define our point P. So the point P needs the radius, the phi angle, and the z to be defined. Okay. Now let us look at the range of all these three. Okay. Now all these have the ranges. The radius can extend from 0 and its limit is infinity. The phi angle, just like I just demonstrated, it goes around from 0 to 360 degrees. I can write 360 degrees as 2 pi. So phi varies from 0 to 2 pi, and z varies from minus infinity to plus infinity. I can have an infinite long cylinder, so hence minus infinity to plus infinity. Now here we have to realize that this point P, like I just said, is an intersection of three planes. One is the r constant plane. Who is the r constant plane? The outside lateral surface area. The lateral surface area of the cylinder, okay, or the lateral surface of the cylinder is nothing but it is a surface which is at constant radius. Anywhere I move around this lateral surface, the radius is going to remain the same. So that becomes a r constant plane. Okay. So let me just use my pen. Okay. So I have here an r constant plane. So this becomes my r constant plane. Remember, in Cartesian coordinate system, you had x, y and z constant planes, three constant planes. Here also, here you have r constant plane. Now, coming to the phi. What is phi? Phi is the angle that is made by between the x-axis and the phi constant plane. The phi constant plane passes through the point. Okay. So, this becomes our phi constant plane. Okay. Now, thirdly, it is the z constant plane. Now, there will be a plane which is at this height of z. Okay. There will be a plane which you will have to visualize, which is placed like as if you are covering the face of the cylinder. You will place the cylinder, you will place a flat plane over this. Okay. And that becomes your z constant plane. Now let us, move away from my drawing to something that is more, neat and clear to understand. So what did I say? I said there's an r constant plane. Please remember that some of the books refer to radius r as a rho. Specifically, if you refer to Heath refers r as a rho. Okay. So you can take this rho, you can read this rho as r itself. Okay. Now, that's one constant plane. The second constant plane is your phi constant plane, which you can see here, the one that is protruding out. And the third one is the z constant plane. An intersection of all these planes will give you the point P. Now, having understood this, now it's time for us to move on to define the unit vectors. Remember, I have explained to you yesterday that the unit vector is a vector which is always moving outside the object, and it is normal to the surface of the object, normal to the tangent drawn to the surface of the object. Okay, so if we go by that definition, let us first consider the r constant plane. Now, if I say there is a unit vector coming out of this cylinder, okay, and it makes an angle, 90 degrees angle, with the surface of it, to the tangent drawn to the surface of the cylinder, okay, then this is called as AR bar. Okay, here we have already defined P is defined by R, phi and Z. Okay, we know the range. R varies from 0 to infinity, phi varies from 0 to 2 pi, Z varies from minus infinity to plus infinity. So, the first unit vector that we have, okay, the first unit vector is AR bar, okay. Now let us consider the phi constant plane. This is the phi constant plane. Just for space constraints, I'll draw the unit vector in the lower side. So this is your phi constant plane. Okay. So phi on the unit vector that is normal to the phi constant plane and moving outward. Remember, phi varies from 0 to 2 pi anti-clockwise. So moving outward, so which will be plus a phi bar? This will be the direction of a phi bar, which is positive. If it moves this way, then it's negative. Okay, so this is minus a phi bar. Okay, so the next one is a phi bar, and the third one will be the unit vector which is normal to the z constant plane. So here I'm adding az bar, positive direction, so that will be az bar, and if it is in the negative direction you have minus az bar. So you have az bar as the next unit vector. Okay, now it's time for us to understand the differential lengths and the differential areas. Okay, just as we have already defined in case of Cartesian, here also if I move an incremental length along the radius, okay, then that defines my dr. Like for example, you saw in the earlier example that I took a hollow cylinder, right? So I had a hollow cylinder. Please don't go by my drawing. So it has some thickness. So if I move from the inner radius to the outer radius, then I have moved a distance of dr. So my first length will be dr. Now I have to define the length along phi direction. Okay, so what will be the length along phi direction? Okay, so I'm going back to my old figure for reference, and I'm now going to cut a section of the cylinder. Okay, I'm going to cut this section of the cylinder, fine, and we are going to redraw it here. Okay, so if I can reconstruct this, this is our z axis. Okay, I'm going to take the x, y and z axis. Okay, and I'm going to get our fellow. So let's get the piece out of it. Okay, so let's say it is something like this, slight curvature, and you have So this is our piece that we have removed from this pipe. Now, like I already explained, when I move from the inner radius to the outer radius, I define what is called as the dr. So dr is my differential radius. Okay. Now, what's the second one? You have phi, length along phi. Let's do the easier one as usual. So let's define the height. Height will be dz. Okay. Now, coming to height along the z direction, height along the, differential length along the radius. We are done with two parameters. Now we have to see what is the length of, what is the differential length along the phi. Okay. So for this, what I will do is remember that phi is an angle. Okay. Now, where is this angle? The angle is with respect to while it has moved from this phi to this phi. Okay. Now, where is this phi? Let us just take a projection of this phi, and if I draw it, okay, this is angle phi 1. Okay, and let's say I take the projection below here. Okay, and this is your phi 2 with respect to the x-axis, right? So you have two angles, phi 1 and phi 2, and this angle will be your d phi. Okay, now this angle is d phi, but what is the differential length along phi? What will be the differential length? What will be this length? Okay, remember this length is the arc length. It is not a normal length. It is the arc length. So the arc length is given by the distance from the reference, that's the radius, into the angular into the angle. So this will be r d phi. Okay, this length will be, arc length will be r. Why r? Because this is the radius that we have been talking about. Okay, this is the radius, so r into d phi, so r d phi. Fine. So now we will include our differential lengths as well. We defined dr. Okay. We defined r d phi, and we also defined dz. Now, having understood the differential lengths, it is not going to be difficult for us to define the areas. Okay. So let us consider this small piece that we have cut out once again. Okay. So if it's okay, then I'll go back to the same one, or let us just erase it. Okay. So what I'm going to do is I'm going to erase this piece from here. Okay, fine. So let's draw this piece once again. Okay, and then define the areas. So for the same coordinates, okay, so I have my z-axis, I have my y-axis, and I have the x-axis. Okay, let's fine. So we have the piece over here. Now we have to define the areas. So I've just turned it for our convenience. Okay, so let us look at this face, the one that is facing us on the outside. Let's consider that area. Okay, so this area will be defined by this length into this length. Okay, so what is this length? This is dz into, you have here r d phi. This is the arc length. So this is our arc length, r d phi, and this is our height. Okay, so you have one area here. So dA equal to dz into r d phi. So I'm going to take the r here, r d phi. Okay, now let's talk about the unit vectors a little later. Okay, associated unit vectors a little later. So this is one of our areas. But which area is it? How do I differentiate? Remember that this particular phase that we are talking is on what plane? Which plane does it talk about? Which plane does it consider? It's an r constant plane. Anywhere I move around on this face, on the outer face here, the radius is constant. So it's a r constant plane. Okay. So this is your DAR. Okay. Now let us consider uh, this phase. Okay. Now this particular phase, let me just, okay, I'm highlighted it, this phase. Now this will be the height into this length. Now what is this length? This is the radius, the thickness. Okay. So dr into dz. So I have dA equal to dr into dz. Now which constant plane is this? This is the phi constant plane. It's as good as you're talking about this. It's as good as you have probably cut this intersection. Okay. So if you have cut this intersection, fine. So if this is the intersection you have cut, then this is the phi plane, right? The phi plane is the constant plane. So this phase comes along the phi constant plane. So I will say dA phi is equal to dr into dz. Finally, I have this phase, okay, on which there are dots. This phase, who is constant here? Z is constant. The radius is varying from the lower radius to outer radius. Okay. And your phi is also varying. So this is a Z constant plane. So I'll say DAZ is equal to this length into this length. So it is the dr into the arc length. Arc length is r d phi. Okay, now these are the areas. Now these are just magnitudes. We now want to convert, or we want to define the area vectors. Okay, so in order to have area vectors, we put associated unit vectors. So here when I say DAR, it's the R constant plane. I will simply write AR bar. It's quite simple. So similarly, DFI, okay, DFI is associated with the phi constant plane, and the unit vector that defines it is in this fashion. So it is into A phi bar. Let me just draw the unit vector here as well. So I have A R bar, right? And thirdly, my last surface. So this surface is the top surface, and the unit vector always moves out from the object and it makes 90 degrees with the object. So I have AZ bar here. Now, what about the other faces? If I take the inner radius, okay, inner face, what's happening there? In the inner face, the area remains the same, but the the direction of AR bar changes. So AR bar, now I'll just redraw here, okay. If we had considered, this length, okay, please excuse my drawing. So if we had considered this length, then this would be AR bar and this would be minus AR bar. Likewise, if I consider the same face again, let me go back to here. If I consider this, the dotted surface where z is constant, then I can define a z bar, and when I consider the lower one, it will be in the direction of minus a z bar. Okay, so here if I have a z bar, I have on the lower side, I will define minus a z bar, right? So, but the area remains the same. Okay, so I can just add here plus minus, and likewise dA phi will be plus minus dr dz a phi bar. dAz bar will be plus minus r dr d phi az bar. So we have now defined points, we have defined the unit vector, differential length, and also the differential area. Now if I have all of this, I can define what we call as differential volume. Okay, differential volume dV will be equal to the product of all the lengths. Which are the lengths? They are over here. So I will write it as r dr d phi dz. That's my differential volume. Okay. Now just as we did yesterday, we will define the vector differential lengths. Okay. Now the vector differential lengths will be sum of the vector lengths. Okay. Now we already know the lengths, but these are the magnitudes. Okay. So for each of the magnitude, I'm going to attach the associated unit vector. Excuse me. Okay. So we consider the associated unit vector. Fine. So I have here, let me call the differential length vector as dl bar, which is equal to, okay, dr ar bar plus r d phi a phi bar plus I have dz a z bar. Now this is the differential length. So with this we have done aspects of cylindrical coordinate system. These are the references that I have used for this lecture. Though they are all electromagnetic books, they have covered the prerequisite of vector analysis and also the coordinate systems. So I recommend that you all go through these books. These books give you a deeper insight of the subject and they are extremely interesting. In this lecture, we have looked at the Cartesian coordinate systems and the cylindrical coordinate systems, and in the upcoming video, I shall be covering spherical coordinate systems. Until then, take care of yourself. This is Dr. Ashwini Kottashetty signing off for now. Thank you.